Hi everyone, and welcome to this presentation on deep learning-based prediction of test input validity for RESTful web APIs. This study has been conducted by Alberto Martín López, Sergio Segura, Luis Valencia Cabrera, Antonio Ruiz Cortés, and finally me, Giuliano Mirabella. We work at the University of Seville, and our research focuses mainly on software testing, especially in the domain of RESTful web APIs. RESTful web APIs, also called simply REST APIs, are powerful interfaces that control specific resources on the web, allowing many systems to interact with each other and share information. They usually provide basic operation of creating, retrieving, updating, and deleting contents, typically implemented by HTTP protocol. This video is composed by three main sections: introduction, approach, and evaluation. To start with, we will talk about API parameters and the challenge we faced in this study. Being complex interfaces, APIs typically provide many methods, which in turn require many input parameters. Those parameters are usually depicted in the documentation of the service, along with their type and a brief description. For example, the operation of getting a YouTube video accepts parameters like the channel type, part, published after, and published before. Another example can be the access to a GitHub repository that handles parameters such as visibility or affiliation. But are API parameters independent? Can they be combined in any way? The answer is no. Let's see an example. When getting a YouTube video, if you specify a value for video duration, then you must also set the parameter type to video. Or in a PayPal transaction, if you include a label, you must also include a custom amount. Finally, in Foursquare API, you should include either the LL and radius parameter or the SW and NE. These logical restrictions among input parameters, called interparameter dependencies, are very common in real-world APIs. In previous studies, we defined a specific language to provide support for those dependencies, called interparameter dependencies language, or IDL for short. Let's see an example of IDL usage. Documentation states that an error will be returned if you specify a value for the location parameter, but does not also specify a value for the location radius. So how is this translated into IDL language? With the sentence all or none of location and location radius. This sentence means that either you include both of them or you don't include any. Another example can be GitHub again. If you use in the same request the parameter type and visibility, or type and affiliation, an error will be returned. So this can be translated in IDL as 0 or 1 of type and visibility, and 0 or 1 of type and affiliation. Last but not least, we have the example of language tool. We can see how the parameter preferred variance is only available when language is set to auto. So the rule in IDL language would be, if preferred variance, then language must be set to auto. So language equals auto. Below, we can read another relation between the parameters enabled only, enabled rules, and enabled categories. Such relation can be translated as if enabled only set to true, then enabled rules or enabled categories. So you must use one of them. Now let's talk about how these interparameter dependencies can jeopardize the task of software testing in the domain of REST APIs and how we address the problem. So the real problem we are facing is as follows. Random testing techniques neglect dependencies. It means that most requests generated are invalid, and ultimately the API does not get tested because it's not running any functionality at all. And how is the approach we propose to solve this problem? Well, random testing techniques neglect dependencies, and again, most requests generated are invalid. But now, and this is the key, we can infer the validity of test cases, and we can select only those calls whose prediction is to be valid, whose outcome is predicted to be valid. In this way, we can test the API correctly. But what can we use to infer the validity of test cases? Well, we can use a deep learning-based classifier. In order to design a deep learning classifier, we have to do basically three things. We have to find a complete dataset with enough information. We have to design an architecture for the network, and then we have to train it. So first of all, our dataset is structured as you're seeing. In each row, you can find an API call, and all columns but the list are API parameters, such as visibility, affiliation, direction, etc. And then we can find the class. The API can be faulty or valid. For the architecture of the network, we tried with several possible configurations, and finally we decided to set 7 layers and 3 dropout layers in between. A key point here is that the architecture is quite flexible. This is because APIs has different number of input parameters. In fact, as you can see, the first layer is set to n possible neurons, which means a variable number of inputs. Finally, to accomplish the training of the network, we performed a simple k-fold validation, which means that the dataset is split into test and training, and the network can be trained and then evaluated on the test data. In order to evaluate our approach, we studied 2 research questions. First of all, how effective is the approach in predicting the validity of RESTful APIs test inputs? And the second is, what is the impact of the size of the dataset in accuracy of the network? By making use of 8 different services of 5 real-world APIs, we could demonstrate that the proposed system could achieve an average score on test data of 97%, the score being even perfect in several services, such as GitHub. To answer the second research question, we retrained the network with smaller datasets and found that the score needs approximately 800 requests to reach 95% of accuracy. After 800 or maybe 1,000 requests, the score increases asymptotically. As a conclusion, we can fairly say that given an average accuracy of 97%, this strategy could be a powerful enhancement for RESTful Web APIs testing, because it allows the requests to be filtered depending on their validity, and without the need of a human manually specifying interparameter dependencies in ideal format. Let's review now what we have learned in this presentation as a reassessment. First of all, we talk about interparameter dependencies and how they may affect the task of RESTful Web APIs testing. Then we described our proposed solution to overcome the previous problem. Then we talk about how to design our deep learning classifier in order to infer the validity of requests. And finally, as a conclusion, we demonstrated that the accuracy of our system is approximately of 97%. Such a high accuracy suggests that this idea is something we should definitely keep working on in future studies. Many thanks for your attention, and please feel free to ask us any question you may have.